Okay, thank you. Good morning, everybody. Welcome to the first lecture on the Higgs Boson. If some of you are regular summer school attendants, you might remember 3 years ago we had Dr. Andrew Hamilton from UCT lecturing on the same subject. But we are delighted to have Dr. Heather Gray here to give a course of lectures on the Higgs boson once again. Heather is actually from South Africa, and she received her BSc and her Master's here from UCT. But because of the specific area that she was interested in, there wasn't a university in South Africa that offered a course. So she went off to the California Institute of Technology to do a PhD. Between 2010 and 2017, she worked at CERN, which is the European Council for Nuclear Research. She worked there as a research fellow on the ATLAS experiment, and she will explain what the ATLAS experiment is. The ATLAS experiment is one of 4 at the Large Hadron Collider at CERN. And she worked there as a staff member, but she was also one of the main contributors to the first physics paper published by ATLAS, in which they measured the number of charged particles produced in the proton-to-proton collisions. She is currently a divisional fellow at Lawrence Berkeley National Laboratory, and she still works at CERN, but now she works for another entity. She will explain all that. And when she's not at work, she can usually be found in the mountains or the oceans. So let us welcome Heather.
That's okay. Thanks very much. Good morning, everybody. Everyone hear me okay? Everyone at the back hear me okay? Yes. All right. So hi, everyone. So first of all, before we get started, I think probably some of you have noticed the aircon's not working right now. The company who are responsible for it, they've been notified, and they're going to come and try and fix it. But I suspect that it's going to be a little bit warm during our first lecture today, unfortunately. We've left all the doors open, and if you get too warm, feel free to step out and get some water or take some air. I won't take it personally if you do that. So let's see what we can do. Hopefully I'm not going to melt here up front. We will see. Okay, so I'm very happy to be here. It's been a while since I was at UCT, and to be able to tell you a little bit about this particle, the Higgs boson. So I made my own introductory slide, but most of it's already been said, just to show a little bit where I've been and where I've worked. So here, of course, we're starting at UCT, and then this is Caltech, where I did my PhD just outside Los Angeles. Here is where CERN is. It's in Switzerland, in Geneva, just on the French-Swiss border. And then now, for the past year, I've been back in California working for Lawrence Berkeley lab. To be honest, I spend about half my time in California and half my time in Switzerland, so I tend to take a lot of flights to do it. And the reason for that is because what I'm going to tell you about, which is the Large Hadron Collider, which is located here. And this is the machine that we use in order to discover and to study the Higgs boson. When I put this slide together, I think what I decided is that I only like to work in beautiful places, at least when I found the pictures. This seems to be at least the theme that I managed to find. And this, of course, is me. And that's actually, I don't know how well you can see it right now, but this is actually me with the ATLAS detector. But that's something we're going to talk about in quite a bit more detail in tomorrow's lecture. So this is a picture of ATLAS. It's something that's going to come up a number of times. Just wanted to show you it. And here, just to give you some scale, this is actually a person. Okay, so we're talking about a really gigantic detector. And it's not only gigantic, it's also extremely precise. And so again, this is something we're going to talk about tomorrow. So I've worked on this experiment, which is called ATLAS, at CERN, which is this big laboratory really located in Europe underneath the French, on the French-Swiss border. And I've been working there about 12 years with various different employers. However, the research that I've been doing has essentially been the same. I've been working on the ATLAS experiment on various different topics. Here's a couple examples. I don't know how well you guys can see the bottom of the screen. Sorry about that. I'll see what I can do for tomorrow's lecture. So I've worked a lot on silicon pixel detectors, something I'll tell you about. Also track reconstruction, which is really trying to figure out when we have particles going through the detector, kind of exactly where they went through. And we need this to figure out some of the physics. I've also worked on the Higgs boson for many years. In particular, for those who might know what a fermion is, my particular speciality is working on studying the coupling of the Higgs to fermions. But don't worry, this lecture I'm not assuming anything. I'm going to explain all these words that I just said really quickly, and hopefully things will become clearer. So yeah, that's the goals of the course. So what I'm trying to do here is to not really tell you everything just on a superficial level. I really want to try and describe in detail so that you get some feeling for really what this Higgs boson is. Also, why it's important. Why did we build this multi-billion-dollar experiment? Why do we have many thousands of physicists who are really dedicating their whole career to studying this? And also talk a bit about the discovery. This was a pretty exciting time, and I was really lucky because really I was there to be able to see this. And this is the sort of discovery that only happens once every maybe 50 years in physics. So it's something that's very rare and something that is very special. One sort of general comment, I enjoy interaction, so please feel free to interrupt and ask questions. It doesn't need to be, we don't need to wait till the end and discuss any questions. I'm happy to take them during the lecture. Sometimes I might say, okay, fine, it's going to be on the next slide. This might happen, but yeah, please do ask whatever you are curious to know about. So this you've probably seen in the schedule. We have 5 lectures this week. And this lecture is really going to focus on trying to give you an introduction to particle physics, sort of tell you a bit about all these different particles that we study, and also to explain kind of what is the Higgs boson. I think explaining what is the Higgs boson without being able to get you guys to do a couple pages of mathematics is very challenging. So you're going to have to bear with me on this. Maybe trust me a little bit that the mathematics actually works out. But this is the goal of today, is that hopefully some of these words I said about the particles will really start to make more sense. Then lecture 2, I'm an experimentalist. So what I do is I actually measure things. This is my primary job. And so here I'm going to tell you about the devices that we actually use to firstly produce Higgs bosons, because they aren't really sitting around. I can't give you a Higgs boson to look at. And also, once we've produced them, how we actually go about measuring them. So these will be the accelerators and the detectors. Then lecture 3, we will talk about one way in which we actually saw the Higgs. Okay? And this is actually using photons, which are light. And so we will talk about the devices we use, how this was done, and really see how this channel actually contributed to the discovery of the Higgs. Next one, a different channel. We'll use heavy particles. I'm not going to tell you what they are right now. This is something will become a bit clearer. And then the final lecture, I'll sort of summarize a bit about where we've come since the discovery of the Higgs, kind of what we know, and kind of maybe think what could be next to do it. So yeah, that's the kind of outline. This is what we're aiming for. But yeah, we will see how everything goes. Okay, so lecture 1, what is the Higgs boson? But before I do that, I just want to check any general questions about the course, anything you want to know? So do feel free to take any pictures you want. I'm not shy. There's nothing secret on our slides. Our research is all open. And also these lectures are being recorded, so you can go back and have a look at them after. Yeah? Sorry, could you speak up a little bit?
Some insight into the mathematics would be nice, even if you couldn't necessarily.
I will try to. I have a few equations that I will show. I'm also happy if you want to spend the time learning a little bit more about it. I can point you towards some material which will actually explain the mathematics in some more detail. So it's about 2 pages of mathematics to really see how the Higgs works. Unfortunately, there's a bit of background behind those 2 pages. But that's the tricky part. The 2 pages are quite... yeah, it's 2 pages after you've done 2 years, right? This is about the feeling. So yeah, no, I'm happy to point people also to extra material. Okay, so I want to sort of, before I talk exactly what the Higgs is, I want to give you an idea about how we think about things. And it may seem kind of simple, the way that I'm doing it, but the point is really to see how the intellectual development has actually happened really from earlier times. And so we're going way back in history. We're going back to many hundreds of years BC, where there were actually two key questions. And these are questions that kind of have been bothering philosophers and eventually scientists for many years. The first question is, we look at this world, right? We have all these different things, yet we kind of have this feeling that there needs to be some sort of underlying structure, which we want to know. And if you sort of say, okay, fine, maybe there could be some structure, then the next two questions you're going to ask is, what really are the fundamental components of the world that we have? Fine, we know the components. And the second question really would be, how would these components interact with each other? Otherwise, it's pretty boring. You're going to have this nice, well-understood world, and nothing's going to change. You need to know how things interact such that you can actually see how various things change. And I like this quote. We don't need to read through it, because I want you to notice the date of it, right, really long ago. And the reason I'm mentioning it is that we were already talking about the term atom there, which is, of course, going to be one of the first answers to the question that I have. By the way, giving a spoiler, it's not going to be the final answer, actually. Of course, the side note is perhaps when Democritus talked about atoms here, he wasn't talking precisely about exactly the same atom we talk about today, but already there was kind of this feeling and this concept that we should be able to sort of say what are things actually made of. And the way I like to think about it is I like to think about we're learning how to play chess. Okay? So if you want to play chess, you actually only need to know two things. You need to know what are the pieces and what are the rules. And then you can take on one of these supercomputers and beat them. Well, maybe not quite. So there is, of course, some subtlety to it. Even if you know the rules, it doesn't necessarily make you a good player. And so this is sort of the metaphor that I like to think about when I'm talking about these things. And sort of making the point more, I wanted to show this because it actually turns out that in the ancient world, we had all these civilizations who had very little contact with each other, yet at the same time, they all came up with the same questions, right? They all said they needed to be something fundamental. And these are the examples. That's the answer from the Greeks. That's the answer from the Chinese and from the Indians. Everybody had this feeling that they needed to be some sort of structure in the world that we had around. And I find that kind of interesting because, sure, the things are a little bit different, but the idea of it is really the same between all these different countries. Okay. So we're going to talk about really small things most of this course, and we're going to be talking about things that you can't see, almost all of them. And so to get there, I want to start with us, okay? And so I found a picture of some engineering students at UCT. Of course, that's not exactly representative of my audience here, but it's just saying, it's close, right? Slight differences. But you are saying things that I'm not saying. Yeah, but we're just going to start with people, okay? And if you ask that question, kind of the first answer you might have, okay, once we've gone through medicine, we'll just brush through medicine quickly. The first answer you might come up with is that people are made of different molecules, right? We all know that we're 99.whatever% water, and there are other different molecules that are inside us. But immediately as soon as you come with this answer, you actually come up with the next question. What are molecules made of? This we know very well. The answer here is atoms. I said they'd come back. And here is a sketch of the periodic table, which is actually showing us all the different elements that we have. And so to some extent, you can basically take all these different elements once you have this table, and you can make up all the different molecules that you have, right? And so that gives us sort of the answer of what are molecules made of. The answer would be actually atoms. But, of course, as you know, this turns out not to really be the final answer, because actually there are things inside. And so here I want to spend a little bit of time, because these are the particles we're going to talk about. And so here we're talking, this is some atom. Okay, it doesn't particularly matter which atom we want. The other thing I want you to pay attention to is the distance scale we're talking about. Okay? we're talking about 10 to the minus 8 centimeters. I'll talk a bit more about, exactly these scales, but you'll notice things get smaller and smaller. Then, as we know very well, inside an atom, there is a nucleus, and there are also electrons. And these electrons are orbiting the nucleus. And this is, of course, a sketch. But the reason that you're kind of seeing these electrons in these orbits is because, of course, we don't actually know precisely where electrons are. This is quantum mechanics. We actually have some probability for an electron to be at some position at a time. We can measure electrons, then we actually get to see, to condense the wave function, see them. But they're actually already here when we're on this level. We start to get to things that are kind of unfamiliar. Because in real life, right, we can't talk about the probability that I'm here. I really am here right now. I'm not partially in Switzerland. Maybe my brain is, but I'm right here. Whereas for electrons, it's really not like that. There is some probability of them being at different parts in space, and this is the same for all these different particles that we're going to talk about. So the first thing you can notice is this sketch is completely wrong, because if you compare the size of the atom to the size of the nucleus, and so here the difference is going to be 4 orders of magnitude, so this would be 10,000, you shouldn't actually be seeing the nucleus at all in the sketch, right? It's 1/10,000th of the size of this atom. This means it's a tiny, tiny prick, okay? So it's much, much smaller than it looks here. But here's the nucleus, and what you can notice is that the nucleus is actually made up of a bunch of different particles, and these ones are the protons and the neutrons. Who's heard of protons and neutrons? Everybody? Excellent. Again, the scale here is not so different. We're just down 1 order of magnitude. However, we actually know now that these protons and neutrons are actually not fundamental. Indeed, if you take one more step down, you actually find that they're made up of quarks, okay? And inside a proton and a neutron, there are actually 3 different quarks. And the properties of these quarks, when you add them up, they actually give you the properties of the proton. So everyone knew about protons. Who's heard of quarks? All right, everybody. Excellent. We're going to keep going through. But then we notice we're down again at another small scale. We're really down at 10 to the minus 16. And actually, this is where we know right now. Okay? This is the smallest particles that we know of. Right now, we think that they're point-like. But as always in science, right, we can think that something is some way. We need to test it, and sometimes things surprise us. So for now, that's what we have. And these are actually the building blocks that we're going to need to really put together the model for the world. Yeah? Yeah. So this is something we'll talk about a little bit later, but the short answer is this is actually color. Okay, it's called color. So you know, for example, that with charged particles, you can have a positively charged particle and a negatively charged particle. Color is something called a quantum number, and this is the same as the concept of charge, except there are actually 3 different types. So the thinking, it's like, there's positive, negative, and something else. And so just to be convenient, it was called color. And so what we talk about is red, green, and blue, basically as ways to label the different states that you can have for the quarks. And if you've heard about the strong force, this is actually the force that will deal with color, which we'll come back to a little bit later. But that's an important property, actually. Yes?
You're showing me the orbits of the electrons in ellipse. Please repeat the question.
Oh, sorry. You also... Okay, sorry. Yes, that's a good point. So the question was, why do I show the orbits of the electrons as an ellipse? So actually, that's because, well, I didn't draw this picture, but whoever drew it was trying to condense a 3D picture flat. And so what it's actually meant to be is it's meant to be, you imagine really a 3D ball with a circular orbit, and then if you look at it straight on, it's going to appear as an ellipse. So it's meant to be looking as a circle. It's meant to be a circle, but in 3 dimensions. Yes?
Please excuse me if this is a very stupid question, but are all those elements that you've shown there, are they all particles? Because in fact, as I understand it, an electron is only a charge. Or am I wrong?
but no, an electron is a bit more than just charge, actually. So elements are made up of atoms, okay? And you get different elements by combining together different number of electrons, different numbers of protons and neutrons, okay, to make them up. And so this is what I meant by the concept of building blocks. Now, an electron is something that's point-like, as far as we know. So what that means, and it's weird, is we think it has no size at all. Okay, we think it's really, every time we look at it, it gets smaller and smaller. And it has charge, that's one of its main properties, but it also has an electronless property, if that makes sense. So what I mean by that is that when you make electrons, I can't just create any number of electrons out of thin air. I actually have to make equal numbers of electrons and positrons. There is this, and so that's what I mean by electronless. It's something that you have to basically get to sum up to really make it. It also has something called spin. All particles actually have a property called spin. And so it's actually a bit more of a concept than just charge. It's really a particle, and one thinks about it as a particle with certain properties. This is a way to think about it. Sure. Okay. So I promised you to remind you about tiny numbers. I'm sure everyone knows this. But actually, the reason I like to show it is because it's really quick to write down something like 10 to the minus 22. Okay? But it's a lot less quick if you actually write it out like this. And this actually gives you a better feeling, but just when you look at it, of really the scales we're talking about here. We're really talking about very, very tiny things that are really impossibly tiny when you think about it. And for example, here's a sort of illustration, is if you imagine I had a meter stick ruler, okay, which is about a meter here, and we put an atom next to it, which is going to be 10 to the minus 18 meters. This is the same comparison as if we actually took a 1 kilometer meter stick, a big one, and we compared it actually to the size of the galaxy. So we're talking really huge distance scales when we actually try the differences, when we try to really look at these tiny particles. And so you can talk about them quite familiarly, but they're actually really, really small, all of these particles. And that's sort of already starting to answer what I'm going to explain to you as to why we need these huge accelerators and detectors. It's because these things are really tiny. Also, they don't stay around very long. This is something else we're going to talk about. So there's something called the Standard Model, and it's a pretty boring name. And the reason it's actually boring is because it was a theory that kind of got put together over sort of the 50s and 60s, and everyone thought that it was just a temporary theory. What they thought is that we were going to come up with another more elegant, more beautiful theory, and it was going to replace it. So why bother? Let's just call it the Standard Model, and then it's going to change. But as it's kind of turned out, and as things have gone on, it's kind of stayed to be really the right theory. And so eventually we actually made a capital S and a capital M, because it seems we're stuck with it. This is the model that we have right now. And so what this is really our current fundamental theory. And because I'm an experimentalist, I need to give you a caveat until proven otherwise. And indeed, that's actually a lot of the work that we're doing, is really trying to prove that the standard theory is not really the standard theory. If you have questions about that, we can talk about it. And it has two components. The first component is matter. And so this is why I mentioned this question about fundamental components. And our answer currently to what the matter is are all these different elementary particles. So these are these quarks that we're talking about, also these electrons. And there's going to be something else called neutrinos. They'll come up in just a bit. Then we have forces, okay? And these are our fundamental forces of nature. And basically what these tell us is really how the different elementary particles actually interact with each other. This is what the forces do. And so these are the sort of the outline. And now what we're going to do over the next few slides is kind of go through all the different particles that we have, both for the matter and the different forces, so that you have some feeling for how this works. So matter has two types, okay? We've talked about them now a bit. We have the quarks, okay, these ones over here. And then we have the electrons, which are a type of lepton. Now you'll notice there are all these different names that come up. They're really just labels, okay? Everything here is actually mathematical equations. And these are just labels that physicists have given them to really make things easier to talk about. So there's no deep meaning, but most of them have some sort of origin behind them. And actually, for example, the lepton, the reason they were called that is because they were very light. And so people naming them took the Greek word for light, and they said, let's call them lepton, just for some sort of light particle. And so that's kind of the origin behind their names. Now, I said I'd mention neutrinos, but unfortunately not much. These are particles. They're also leptons, so like electrons, but they're pretty weird and interesting particles. And we thought for a very long time that neutrinos had no mass at all, but we learned over the kind of past 10 years or so that they do have mass, so we were wrong about that. That's exciting. We actually like to be wrong. And so they're actually something that's really quite an active field of research these days. But they're not really going to come into this course too much. I just wanted to mention them so that you're familiar with all the different types of particles. Sorry? These ones. Yeah, so the question was, what are the black balls inside the nucleus? These are the neutrons. I mean, this is all visualization, right? You can actually, by the way, you can actually look at individual atoms now. So if you have a super fancy electron microscope, you can actually resolve individual atoms, but you can't actually see further down. This is actually not possible. So everything I'm telling you, you have to sort of imagine this is people trying to explain how this works, but we actually can't look at these things, at least not with a conventional way that we might actually look at this sort of thing. Yes?
Photon. Photon. What is it?
Haha, it's still coming. So the photon is going to be one of our force-carrying particles, which we haven't got to the forces yet. We're just on the matter. We'll come back to that.
So neutrons and neutrinos are not, they're not the same?
There is absolutely no relation. They just happen to have similar names.
Okay.
So a neutron is sort of a brother of a proton. A neutron is made up of 3 quarks, as is a proton, but they're different quarks, and that's how they have different particles. And a neutron is uncharged. So that's the main difference between protons and neutrons. A proton is charged, and a neutron is uncharged. Neutrino, nothing to do with it. Sure. Yes?
The neutron has no charge. The proton will have a positive charge. What about the electron?
Has a negative charge. So what you need to do, right, when you're making your atoms, is you actually need to have the right number of electrons to balance out the positive charge of the proton, and that's how you end up getting electrically neutral atoms by themselves.
So why do we need neutrinos at all?
This I have to come back to later. This is going to relate to the weak force, which is another one of the forces that we have. But they're going to be, actually, the next slide I'm going to show you other things we don't need. This is one of the reasons why physicists are not so comfortable with the Standard Model, is there seem to be extra bits that we could do without. And that's kind of a little bit unsettling when you're talking about a fundamental theory. Yes?
Many years ago, they tried to explain what the electron was to us. And the analogy he drew, and I just want to get it right, they were hunting tigers in India. And they were surrounded by tigerish mist. So they put out their guns and they blew right at the sky, lots of guns, and suddenly a tiger fell from the sky, dead on the ground. That was the electron. You don't see the electron until you hit it with something.
So it's a great analogy. I have not heard it before. I like it. What they're trying to talk about is what I was explaining about the fact that electrons are kind of everywhere. And what they're trying to illustrate by this whole shooting down a tiger, if everyone didn't hear it, was about, if you shoot around the tigerness and eventually you get a tiger falling from the sky. The point is actually the active measurement changes the system. So for example, if I want to go and measure, is there an electron here? I can do that. And I will find an electron at some point. But once I've done that, it's not the same system, actually, as what I had before. And so that's what it's talking about. That's kind of, I like the analogy. It's quite good. Okay. So now, as I promised, there's something weird. Okay. There are going to be many weird things, I think, in these lectures. There's probably a theme. And the problem is that we have a nice set of particles, and we can pretty much make everything that we see in the world, but it turns out that's not all of them. We actually have a set of clones. So what I mean by this, I have a little triangle that's in the wrong place. I'll fix that later. So what we've been talking about so far is we've been talking about the leptons, right? And the example we had was the electron and its neutrino. Okay, so this is the neutrino, and actually neutrinos have flavors. So you were asking a little bit about, what an electron is, this electronless property. This neutrino actually also has an electronless property. So these two are related. And actually you can make everything you want just with these and the corresponding quarks that go with them. But what actually turns out in nature is we actually have 3 generations. So we actually have copies of these particles. So we have an electron, we have a copy of it, it's heavier, that's why it's got a bigger circle, it's called a muon, and we also have a muon neutrino. And we don't just have one copy, we actually have another copy, and the particle here is called a tau, and again a tau neutrino. And so this is something that no one expected. It was really a surprise, because you really don't need to see it. And the weird part is that everything around us is not made of these. So you can make these particles, no problem, it's pretty easy. Some of them you can make in the universe, for example, in cosmic rays. But as to why we need them, it's really unclear. And it's even weirder, because here we actually start to look at the quarks, okay? And so quarks are going to have names, we'll talk about them in a second. But just like the leptons, there are 3 generations. There's the first generation, the second generation, and the third. And the proton and the neutron, remember we were talking about how they're made of quarks, they're all made of these up and down quarks. You don't need these other quarks to make them, and this makes all the atoms, makes all the elements, makes everything that we see. And so yet again, we see we have these copies, and we really actually don't know why this is. So you can ask this question, and actually it turns out this is a deep question. We know that there really are these copies of the quarks and leptons, but we actually really do not know at all why. And as I was saying, we just need up and down quarks to make ordinary matter, but experimentally we know that these other particles exist. Now I see a few confused faces. That's actually my intention, because I want to show you not just what we know, but also show you what we don't know. Because actually that's the point of science, right? What we're after is trying to answer the questions that we don't know the answer to. Not to really just go through the things we know. We're trying to figure it out. And yeah, this is something we don't know. Okay, one question over there.
I just wondered about your choice of colours when you said quarks were blue, red, and green. Now you've done generation 1, 2, and 3 in those particular colours. Is that significant?
No. So this picture I didn't draw. I took it from somewhere on the internet. But here it's just colors to be pretty. There is no significance in these colors. It's really the names. So for example, like the electron, the muon, and the tau, that's kind of the label that we're talking about. The leptons, they have no color. They only have charge. Color is something that's a property of the quarks. And each of these quarks can be either red, green, or blue. And actually can be anti-red, anti-green, and anti-blue. Well, don't worry. We can always make things opposites. This always happens. Yes?
You're talking about generation 1, 2, and 3. Are you meaning that generation 2 is generated from generation 1, generation 3 from generation 2?
Not as far as we know. This is what people hoped, actually, because if, for example, if you look in chemistry, you often get excited states of things. You can have a ground state of something, and then you can add some energy, and you get an excited state, and that would remove the copy. No, here they're actually different particles. So they really are different particles, but they behave in the same way, except these ones are heavier. The only difference between the generations is actually the mass of the particles. Yeah?
So the standard model doesn't predict generation 2 and 3?
Not in the slightest. We do know, for example, that if we didn't have them, a number of our measurements wouldn't work. So in a sense, basically, once we started measuring a few things and we kind of did the rates of various different interactions between particles, we actually found they didn't quite work. So there was a little bit of a prediction, in particular, of this generation of quarks. But actually, the muon, for example, this was a complete surprise. This was just, they found a particle. Actually, they thought it was a quark, I think, initially. Then they found out, oh, no, it's actually a lepton, because it was really not needed. Yeah?
How on earth do you weigh and measure these?
With a lot of difficulty, actually. I think we should come back to that question later, because actually most of this course is going to be about mass. Because, of course, that's what the Higgs boson does. So remind me if I don't come back to it. Ask me later in the course. But it's exactly right. We do not have a scale. In fact, all of these, they live for a fraction of a second. So It's not simple to know how to weigh things. Sorry, she was next. Oh, these are just labels. So you know, like we called something an electron and a muon? These are just labels, and I'll have a slide about these names, because they get weirder, by the way, as you get up. Yes, sorry.
Some didn't figure out if you've made up additional particles, it's made some fit.
Sorry, I didn't hear. Could you repeat?
You summed it all add up. So you put other particles in so that they'll add up.
Yes.
But you don't know they exist.
Oh, we do. Oh, yes. I don't really have it in the course, but for example, for these particles, you can actually really measure them precisely. So we're quite sure these particles exist. They could be, there could be something inside them that makes these particles. This can be, but we're dead sure that these exist. They're very, in a way, it's very clear that they do.
If you say that all atoms made out of up and down quarks, then where do the muons and the other ones fit if they don't make up any matter? They can't float around free. Quarks can't float around.
So that is exactly right. And so the question was, if all matter is made up of up and down quarks and electrons and electron neutrinos, where are these other particles? Because quarks, for example, can't float around free. So, where are these and how do we actually see them? So the answer is that muons, by the way, can float around free. Okay? And actually we see them in cosmic rays. So actually right now you have muons coming through you. You also have neutrinos coming through you. It's okay, it's not going to do anything, but if we put a detector in the room, we could actually see them. So that's the first answer. There are plenty of them, especially the neutrinos. Neutrinos are really everywhere. For the quarks, you are exactly right. Because of the strong force, there is no such thing as an isolated quark. This does not exist. And so these actually exist when we make them at accelerators. So we actually can collide certain particles together, we can produce them, we can measure them, and then they disappear. Now, probably they could make atoms, actually. The problem is that all elementary particles have a lifetime, okay? And what that means is that with a lifetime, once you get to the end of it, the particle's gone. It decays to something else. And the trouble is these ones have very short lifetimes, so short that they actually don't get a chance to actually find other particles and make, for example, atoms. So the reason we can't actually really make atoms out of them is because of the lifetime. So that's the reason. There's nothing more fundamental than that. Yes? Sure.
These various symbols you put in the upper rectangle and the lower rectangle.
Yeah.
Some of them, I know what they mean, like the E means electron and the U means mu. But could you please mention the full name of each of those?
So these ones I have a slide coming, so just be patient. And this is a nu. It's a Greek letter N, okay? And the reason we use the Greek letter N is because it's neutrino.
What is the V part of it?
Sorry,
The upper part is it looks like.
this is the nu.
The V, she's asking.
The V is the nu. It's the letter N in Greek.
Thank you.
So it's just, it looks like this. It's just a letter N in Greek. Think of it as an N. The problem is we ran out of English letters, and so we started using Greek letters. Actually, now we've run out of those, so we use even weirder ones sometimes. Okay, we better keep going. So here you go. This is going to answer your questions about the quarks, okay? And it turns out they actually have really silly names. So at the beginning, when there were only two quarks around, it was pretty simple. We called them up and down. But then we had this extra particle, and this is sort of answering a little bit about how we know the quarks exist, which is a particle called a kaon, and it had a very strangely long lifetime. And the reason it had this strangely long lifetime is that inside a kaon was actually a strange quark. And this has a property that it actually ended up giving it a longer lifetime. So people thought this was odd, let's call this particle strange. Then there was another one which was found, and someone thought it was cute to call it the charm quark, so that became the fourth one. And then finally we had the T and the B that you saw on the sketch, and they were initially called truth and beauty, but actually physicists, we tend to be kind of practical, and people thought this was a bit too sort of, artificial or funny feeling. So these days they're most often called top and bottom quarks. And so the names actually are up, down, strange and charm, top and bottom. Yep, that's what they're called. And yes, the one advantage of this is when you give talks, you can have some amusing titles and plays on words when you have all these different names to do. Yeah, so maybe the answer is physicists have a sense of humor. I don't know. That's what they're called. By the way, this link, I'll put my slides somewhere. I'll put a link in the next lecture so you can see them. There's actually a company who make you soft toys of the whole Standard Model. So you can actually buy all the particles, give them to your grandchildren or nephews and nieces, and they're actually all of them. So I own a couple of them. I own the Higgs Boson, actually. They're kind of fun. Okay, so that was a while talking about all the pieces, but it's important. But in our chess game analogy, we're actually pretty boring still. We have a bunch of pieces, but we actually don't know what to do with them, right? We have all their names, they all sit around. So this is, of course, when we're going to need the forces. So the concept of forces is something kind of familiar. Of course, you've thought about planetary orbits, right? And actually, the movement of planets that you see in the sky, this is really fully determined by the gravitational force, right? So there's one massive object, there's another massive object, there's a force between them, and this actually makes the planets move in their characteristic orbits. And actually, it's the same idea for forces, right? So forces are going to be these things between different particles, and they're actually going to make movement. And this is going to make things interesting. Now, there are 4 fundamental forces that we have in the Standard Model. First one's easy, you know it. It's gravitation. Actually, I say that kind of fast because actually gravitation is the one that gives us the most trouble. When you see the full Standard Model, you will notice that we conveniently ignore gravitation. That's actually because we don't know what to do with it right now. This is a very interesting and problematic point. Then there is electromagnetism. This is something fairly familiar. This is giving us our lights, right? It's giving us our magnets, all of these things. We use this extensively throughout the world. Then there are 2 weirder forces. They are both nuclear forces, so that's why we're not so familiar with them. One is called the weak nuclear force, and the other one is called the strong nuclear force. And these are the 4 forces, that's it. Once you have these 4 forces, you basically have everything that you need in the Standard Model. Now, for those who can actually see the bottom of the screen, you'll notice that there's something sitting on the bottom here, under each of the forces. And that's actually because, and it's something I'll talk about in the next couple slides, is we actually have the concept of a particle carrying a force when we talk about particle physics. So it's not really the case that there's this force sort of sitting around. There's actually a particle associated with them, and they each have names. So for gravity, there is the graviton. That's fairly obvious. Photon, everyone knows. This is our particle that is light. For the weak force, there are going to be some that I tell you about, which are called the W and the Z bosons. These don't actually stand for anything. They're just called the W and the Z. That's their full name. And then finally, for the strong force, they're going to be gluons. And the idea here is because the strong force is so strong of keeping things together, the idea is that they're gluing together nuclei. That's kind of where the name for a gluon actually comes from. And so these are the 4. As I said, I'm going to ignore gravity from now on. Yeah? That's exactly the problem. So the exact problem that we have is that particle physics, the question was, how is the particle, the graviton, consistent with the idea of space-time curvature, right? So basically general relativity and Einstein's equations. Now the problem is particle physics, everything that I'm telling you about is based on quantum mechanics, okay? This is what I meant by, these probabilities of particles being somewhere. And as of now, we absolutely cannot find a quantum theory of gravity. So we have found no way to take general relativity, which seems to work just fine, quantum mechanics, which seems to work just fine, but if you put the 2 together, it just makes complete nonsense. And so this is actually the problem, and so there's no answer to that one. That's an open question, has been many people's research, but yeah, no answer so far.
Following on from that, you're talking about the wormhole, correct?
That is in general relativity. So wormhole is something that you have purely in general relativity. No, so quantum mechanics is basically really when you need to actually quantize a field. And so what that means is that you actually need to put particles in to describe the field in your equation. So it's a sort of mathematical procedure that you have. And it really gives absolutely horrible things with gravity. You get infinities all over the place, which essentially tells you that you don't know what you're doing with your mathematics. This is what we have. This is all general relativity. That's all fine. No problems that we see there. It's when you put quantum together. That's when the problem comes in. Maybe you've heard a mention of string theory. Anyone heard of that? So string theory is many people's attempts to try and put the two together, but so far this looks like very nice mathematics. It's unclear how it relates to the world. This is the current problem. There was a question, yes, at the back there.
If the protons in the nucleus of an atom are positively charged, why then do they not repel each other?
They do repel each other. The reason that they don't fly apart is because of the strong force. So it turns out, and actually I have them ordered in strength, by the way, here, the strong force is actually extremely powerful. It's actually more powerful than the electromagnetic force, and so it can overcome this force. So they do repel each other, but the strong force is much, much stronger. The strong force is pretty strong. It's pretty scary. Question at the front.
Am I missing something? Because the issue of electromagnetism and photon, that electromagnetism is a wave, and photon is a particle and a wave. I'm a bit of a confusion in my head about the two elements there. Could you slightly expand on it?
So I have slides and 2 slides about this. We'll come back to that one.
Okay.
Okay, well, there was a question, one more at the back somewhere? No. Okay, we'll keep going. Oh, here we go. Okay, so this is the wave-particle duality. And this is a really strange feature of quantum mechanics. And basically what it is that all these forces and all these force-carrying particles, they're actually simultaneously a particle and a wave. So what that means, in a way, is that they have properties of particles and they have properties of waves at the same time. And what you tend to do is one tends to think about it in whichever one is more convenient for what one's doing. So for example, I usually think about them as particles, because normally I'm making these particles, I'm measuring these particles, this is what I'm doing. But at the same time, I know that I don't know exactly where it is. And so one just has to accept that it's a wave, and it has, this is meant to be a sort of shape of where the particle actually is. This is what this is trying to show you, and it's saying because the amplitude is higher here, it has a higher probability of being here. But this is just something one sort of learns to live with. It's basically, I think, with quantum mechanics, one needs to accept it's weird. It doesn't really relate to everything else we experience, but you kind of get used to it the more time you spend with it. This is how it works for me. It's weird. Okay, so here was the example of a field. Here was an example of the particle. And in some sense, you can actually think about this field being particles moving between each other. And in particle physics, which is what we're going to be talking about this week, it's usually going to be easier to think about it as particles. Okay? That's mostly what we're going to do, but we're not going to forget that there actually are fields. The reason you want to think of it as a field is you imagine if you have an electron kind of moving through a field, you could imagine that it would actually feel some force, right? But the other way you can think about it is here's one electron, here's another electron, they exchange a photon, and that actually makes them change the direction that they're moving. So these are the 2 ways you can think about it, yes?
Why is your particle in 3 colors, red, black, and blue?
Sorry, this is just because, this is no meaning again. This is just because I didn't want the slide to be all black. Yes?
What do you mean it? Say it's properties of particles and waves.
So I used the word it because I didn't want to use the word particle or wave. So as I was trying to say, this was me just trying to say it can be either, and so I need to use the word it. And it's all these force-carrying particles. And also actually, basically any quantum mechanical particle has some wave-like properties. So for example, if you've heard of diffraction, this is something you can actually do with all these particles, and you can actually, if you pass them through a slit, you can actually see some of these diffractive properties. Okay, so now we're going to talk a little bit about the forces. As I said, we got rid of gravity. That was easy. And we're going to start with the electromagnetic force, because this is probably the most familiar one. The way this one works is that it acts on any particle which has charge. Okay? So if your particle has charge, it feels the electromagnetic force. In fact, if your particle doesn't have charge, it doesn't feel the electromagnetic force. And it's really transmitted by the photon, as we mentioned. Now, one thing to know is actually the mass of the force-carrying particle is important, because a photon is massless, as far as we know. And this means that the electromagnetic force actually can act over an infinite range. Okay? This will not be the case for all the different forces. And of course, the electromagnetic force these days we use extensively in everything. Right? We're talking about lights, we're talking about communication, we're talking about radio signals. This is really a force that I would say that humankind has got to know pretty well, and we've got to use it for a wide range of applications. Weirder forces, the strong force. So we mentioned this, the fact that the strong force actually acts on all particles that have color. And what we need the strong force for is actually to bind together the protons and the nucleons in the nucleus, like you were asking about. As I mentioned, it has a carrier, which is the gluon. And here, these colors are on purpose for everyone who's been keeping track of the colors, because these are really the three different properties, just like charge, that you can have of particles which feel the strong force. So the way it works is that all colored particles, they feel the strong force, and particles can be either red, green, or blue. And the gluon actually, by the way, also turns out to be colored. And so this is something a little bit different to the photon. The photon doesn't have charge, whereas the gluon actually has color. And so these are some of the different properties of the forces. Yeah?
From my physics, which stopped very strongly after Newton, I'm afraid.
Okay.
I kind of got the strong feeling that electricity, electric charge, and gravity are inverse square distance.
Mm-hmm.
The strong force obviously acts over a much shorter distance. Is there a simple law like that? Or is the question an observation?
It's a good question. It's something that gets studied extensively, but it's absolutely not inverse squared. Because otherwise, we would see the world actually collapsing, by the way, because the strong force...
If it's a power law, it must be a higher power.
No, it's even weirder than that. It has this property called confinement, which actually means that it goes the opposite direction to the other forces. The further things go apart, the stronger the force gets, not the weaker. Hold on, I will show you a slide. I said these are weird forces. These are weird forces. And by the way, here's a fun fact. I'll talk about it again later, but just to tell you that actually the strong force is actually the origin of most of the mass of everyday objects, not the Higgs boson. So when someone tells you that the Higgs boson is the origin of all mass, you should tell them that's not actually true. We'll come back to why that is later, but just something I wanted to mention now. So here's the answer to your question. So both gravity and electromagnetism decreases with this inverse square power law the further the objects are separated. Actually, the strong force is a lot more like a rubber band. So if you imagine you have one particle and another particle in a rubber band connecting them, basically it gets stronger the further that particles separate. Okay? Now you say, wait, that sounds weird. What happens if you take them really, really far apart? Actually, what happens is eventually the band breaks, but what you get is two more particles that get created out of that energy that's released. And so then you'll have one particle here, another particle there, connected by a band, another particle here and there, connected by a band. So it's a really completely different behavior that you actually get out of the strong force, and that's actually the reason why we kind of don't know about it. It's because it's really confined to being inside something. It's a weird force.
So when you split an atom,
yeah,
I mean, you would expect that neutron, so the two protons should be pushed apart by simple electric force, but the strong force holds them together. But once they get a certain distance apart,
once you've actually broken this rubber band, right, and made these two sets, then they're not really feeling each other because the band is actually connecting the two together. But there's one more force we need. It's also important if you want to think about splitting the atom, and this one is the weak force, okay? It acts on both charged and neutral particles, but its special feature is it can actually change the flavor of particles. Now, what I mean by flavor here is all these labels I've been talking about for particles. It can actually change the label of a particle. This is what the weak force can do. And here we mentioned that we have these W and Z bosons. They carry it. And it actually has a very short range. And the reason is not because of the strong force. This one's a bit more like the other forces. The actual issue is that the W and the Z bosons are really heavy. Fun fact, that's why the sun shines. It's actually the weak force, which is allowing decays within the sun, that's actually making all the energy that you actually see, which is the light that you actually see from the sun. So the weak force is actually pretty important. So I'm going to actually stop now, because we actually really got to the end of our lecture. We'll talk more about the Higgs next time. But I wanted to conclude by showing you sort of relative strength of the forces. Okay? Now, I'm a scientist, so there's some caveats in what I'm saying here. The first one is you have to decide what distance you're at, okay? And the answer is different depending on what distance you look at. But here is a typical distance, on a sort of atomic scale. And the strong force is 137 times stronger than the electromagnetic force. It is 10 to the 6 times stronger than the weak force, and 10 to the 38 times stronger than gravity. Remember those zeros I showed you? Think about 38 zeros right now, right? We're talking really a huge difference. And so you can kind of imagine this apple falling from the tree going 10 to the 38 times faster. And so that's kind of one of the weird features, is these forces are extremely powerful, yet something that we really don't see at all on a day-to-day kind of basis. Okay, we'll stop here for today. I'll tell you more about the Higgs next time. But let's see if there are any last questions that anyone wants to ask. Yes, go ahead. Yes, I will put them online, and tomorrow I'll put the link in the lectures so that you can see them. They're not online right now, otherwise I would tell you the link at the moment.
When you say it's online, you mean put it on YouTube?
No, I will put the PDF online so you can download the slides. They're also being recorded. Oh, I'll put them on my website, and I'll send you a link. So basically, I'll give you a link you can type into a web browser, and you'll be able to see the slides. I will make it clear, I promise. So one last thing before everyone runs away. I was asked to tell you guys that there's also a film program as part of the summer school. And there's 3 films today. So there's the Enigmatic Dodo at 11:15. There's the Wings of the Dove at 1:15. And then at 3:30, there is Equus in Africa and The Last Horses of the Namib. These are 3:30. And they'll all be in Lecture Theatre 1. So I'll leave the paper at the front here if anyone wants to have a look. But just to tell everyone, thanks everybody.